Hi guys. So far our programs written in machine code or assembly code had in particular annoying limitation when it came to showing what is a computed result. We didn't have any output routine. We used instead the exit code, and this has the limitation on Unix that it's truncated to 8 bits. And for input, or instead of input, we were just hard coding certain constants into our program. That means if we wanted to use a different input for integers, we had to change the program. We had to change this hard-coded initial value. And we certainly need to change that first for going any further. And in this video, I will show you first how to read in some unsigned integer. And in the second part, I will show you how to print an unsigned integer. You will see that the ideas will be kind of similar, but printing the unsigned integer is slightly more difficult. Although this is a very simple problem to read in an unsigned integer, where you probably would use a more direct approach to come up with an algorithm and from there to an implementation. I want to begin with a very special case, see then some pattern in how I solve this special case, and so do this really step by step. Let's assume the user types in 1, 2, 3 and then hits return. And I get a certain sequence of characters. And in the end, after I do certain instructions, I want to have the numerical value 123 in register 1. And register 2 will be used for intermediate results. I will use it as a utility register. So in a first step, I will just initialize this destination register so that it has a well-defined initial state, and let's initialize it with 0. Then in a next step, I will read in a character from the keyboard. So this will be the ASCII value of this character 1. And then I have to convert it to its numerical value. And I can do that by subtracting the ASCII code for character 0. And then I somehow have to copy this to the destination register. Actually, the right position would be the place where it finally belongs to, this position for the hundreds. But I will just copy it to the destination register. And then by reading the next character, shift it to the left. So this step here is kind of surprising because it means that, first of all, I don't have to initialize this register first if I'm overwriting it anyway. And you will also see that this step needs to be overthought in a more general way to do this reading of an integer. Okay, but anyway, the next step would be to read the next character, the character 2, again convert it to its numerical value, and then I do this left shift in decimal terms of this destination register, that I left shift this decimal digit one place to the left by multiplying it with 10, and then I add the numerical value 2. And then I have 12 in the destination register, and then you already maybe see the idea. The next step, of course, would be to read in this character 3, get its numerical value, left shift the decimal representation in the destination register by multiplying it with 10, and then add this numerical value 3. And then I would read in this new line, and of course, this in general indicates that I'm done with reading in an unsigned integer. Here I just have written down these single steps that were applied in this special case, and now we have to find the general case in here. And of course you see that certain steps were just repeated, certain group of steps, these groups. And in this group here, we have a slight difference. This updating of the destination register is done here differently. But now it makes sense why I zero initialized the destination register first, because that means I actually could use here the same update step. And then you see how to realize this in general with a loop. You first zero initialize the destination register, then you read in some character, and then you check whether it's a digit or not. And if it's not a digit, then you're done. And otherwise, you compute the numerical value of the digit, you update the destination register, and then you continue with reading in the next character. And that's what I will show you in the demo. Not handled here, of course, are certain error cases where a user doesn't type in some digit at all, just types in return, or uses leading zeros, which usually should be treated as an octal representation. For this demo, I created a new directory in the variants directory of the Ulm generator. So a new computer architecture will be described here. And initially, this instruction set architecture is just a copy of the last session. So here we also have this instruction for jump above and jump below. And I will need a few more instructions, as you will see. I will now just implement this algorithm box by box, this flowchart, and then afterwards extend it, this instruction set architecture for whatever is needed. So I begin first with some notations or shortcuts for convenience. I want to use the symbol dest for the literal one, for the destination register, and ch for character should be equivalent to 2. And then I begin in the text segment, which is actually anyway the default segment, with initializing this destination register. So for that I use the load 0 extended word to quad register instruction and 0 initialize it. And of course you can use some comments. Here I think it's still kind of clear. Then I read in a character with get character and store this in register ch. Then I have to check whether it's a digit or not. And here I actually also want to use in the demo some comment. If this register contains a ASCII value which is smaller than the ASCII value of the 0 character, then we are done. And we are also done if this ASCII value is larger than the ASCII value of this character 9. Now to check the first condition, I'm subtracting the ASCII code of the character 0 from ch, store the result in the 0 register. And if it's not a digit, then jump below can be used to jump to the vault instruction. Actually, or you can insert it here, label it with done, vault, and then I want to use the exit code stored in the destination register. And in the other case, I'm subtracting the ASCII code of the character 9, also from, of course, the register ch, store it also in the 0 register, and here I use the jump above instruction. And now I already handled the case that a non-digit was typed in. Now I have to compute a numerical value, and then you actually will see a certain kind of optimization already could be applied now, which I will not do. For computing this numerical value, I have to subtract the ASCII code for the character 0 from ch and store this in the same register. That means if I would have switched this to blocks here, I could have used here as destination register, not the 0 register, but instead that. But a rule of experience is do optimizations after you have something which is working, and not before you finish the first step of achieving the goal. Okay, so I just strictly follow the rules dictated in the flowchart. After I computed the numerical value, I have to update the destination register. For that, I could use an instruction which is doing two things, multiplying the destination register with 10 and also adding the content of a other register. I mean, we can describe our own instruction set. Of course, we could provide some mul10 add instruction, but I will not do that because we want to have reusable instructions, and we are limited to 256 instructions. And if we would come up for every special case with a new instruction, we would run out of the possibilities. So I will do this in two steps. I will first multiply the register, the destination register with 10. So with the IMALQ instruction, and here I can specify the literal 10. I want to multiply this 10 with the destination register and also store this in the destination register. And then I'm adding this numerical value of the typed in character digit, which is now already converted to its numerical value, to this destination register. And after that, I have to read in the next character. So I'm doing a jump to the label read, which will be defined now here. And now you see there are actually a few new instructions that we haven't defined so far, and also this here is kind of wrong. We have 3 address machines, so I also have to specify the destination register. Our add queue instruction here is adding an immediate value to a register. What we need here is adding a register to a register. So this is something we don't provide so far. So don't get confused that the same mnemonic is used here. It's a different kind of instruction. And also this IMALQ, here we have the opposite case. So far we just can multiply registers together and then store it in a register. So we need actually this 2 instructions a bit different. So I just copy this and change it. So this will get opcode hex OE, and here goes an F. And in the assembly notation, I distinguish it by the usual convention that a percent indicates that some argument, some operand is used as a register or addressing a register. And in the micro instruction, I'm using here ulm recval x, and here I'm doing the reverse thing. I'm removing here in the assembly notation this percentage sign, and have here a multiplication with an immediate value. Okay, but that's it. And then we regenerate the ulm and see if something needs to be fixed. So this is the new generated assembler, and now we run it on the new generated computer architecture. Type in 1, 2, 3. Let's begin with the special case that we started with. And that's it. And for problems where the exe code would not be sufficient to check results, let's use the debugger. I think we don't have to see the memory in this example. And let's say the user types in 1193046. This will have a nice representation in hex. Now let's see how this program actually is carrying out this algorithm that we described in the flowchart. First, this destination register gets 0 initialized. Then we read in a character from the standard in. So from the buffer, this 1 should disappear. And here you see the ASCII value. And now we will check with the next 4 instruction whether this is a digit, which will be the case. So I just go over this here. And now we will compute the numerical value. So this should become a hex 1. And then we multiply the destination register with 10. We will see here no effect. And then we add this numerical value to the destination register. So yes, of course, we get 1. Now we read in the next character, so this one should disappear. Again, we should get this ASCII value for it. Then again, we check whether it's a digit, and then we again compute a numerical value, should be again 1. Now we will see an effect. This here gets multiplied with 10. In hex, we should see a digit A. Then we add 1, so this should become hex B. And then we read in the next character, so this 9 should disappear, and then we see here a different ASCII code, the ASCII code for 9. Then again we check whether it's a digit and so on. Now again the numerical value, again we multiply this with 10 and add this. Now let's just let's run the program until it hits the halt instruction. Then you see we get actually this value in register 1, and in hex, as I said, it has a nice representation. That's it for the first part for doing input-output with unsigned integers. On the website I will show you a different way to express this algorithm, not with flowcharts, but instead with some pseudocode, where you will find terms like while and if. And this pseudocode will be very similar to what you see actually in C. And for us, for programming in assembly, actually we could use C code as a pseudocode description, telling us what we should do in our assembly program.